all of you and your families are well. To put the focus on what is going to be discussed in this talk, I will try to do that the viewers are able to understand or at least get an idea of how the image is made through two or more photon techniques. I emphasize that these are techniques to make images in biological samples. That is in cells, in the brain to see neuronal activity, in the cornea, and some others. First of all, I want to review a couple of key aspects for this talk. A photon is the elementary particle responsible for the quantum manifestation of the electromagnetic phenomenon. But come on, it is the light that we see. Besides, it is going to be characterized by the frequency or wavelength that it has. Therefore, the higher the frequency, or what is the same, the lower the wavelength, it will have more energy. In linear optics, the idea is that in these processes, light that is emitted by the medium has a similar frequency to the one that we excite. That's why there are linear processes. They don't change so much with the frequency at which we operate. There are a lot of processes that are very common in nature, like reflection, transmission, but we are going to focus on this talk about the process of fluorescence that we will now explain, which is very much used to make image. It's very important to remember that the most of the linear processes don't change the wavelength, so we have to take this into account. When we try to make an image, what we do is illuminate the sample and pick up a signal generated by the sample. But of course, when we illuminate the sample, several things happen. First of all, the electrons jumps to the fundamental level to an excited level in the sample. But of course, the molecule wants to get relaxed as fast as possible. And it has three ways to go back. Directly emitting a photon and losing their energy to reach the fundamental level, which we will call fluorescence, the dark blue of this picture. We go directly from the excited state to the fundamental state, emitting this photon. Another possibility that they have is go to an intermediate state, which we will call to a triplet state, and then decay to the fundamental by emitting a photon. This process is what we call phosphorescence. Go from the excited state S1 to a triplet state, and next to the fundamental emitting a photon. And finally, it can also happen that there are electrons, that the electrons that are in the excited level lose their energy through a non-radiative process. This means thermalizing, losing heat, or something like that. This type of non-radiative process are the ones that we don't want. Non-radiative means not emitting photon. So we are going to focus on the process of fluorescence, in which first the electron is directly excited by acquiring the energy of a photon, and it's relaxed by an inverse process, in which it emits a photon to go down to the fundamental. So the question that comes now is, the frequency which we emit photons is the same that the frequency which we receive them? If so, we will not be able to identify with your detector which one comes from your sources or which one comes from the sample. What we are seeing here is an emission and excitation spectrum. We excitate the sample at 480, and in the process of relaxing, it emits at 550 nanometers. So we have a difference between the emission and excitation of 70 nanometers, which will help us to identify them. This difference is technically called stock shift, and it is very important that it should be as large as possible, because it will help us to identify more photons coming from the sample. In fact, when the stock shift is very small, the absorption and emission curves comes together and give rise to a spectral overlap, in which it is impossible to detect where each one comes from. Well, can be resolved changing the setup configuration, but it is still a problem. In this image, we see a fluorescent substance that we have illuminated to create this fluorescent. As we see, the whole sample has been illuminated, and it is emitting this fluorescent. This a priori, it's good, it's okay, we have fluorescent. It is what we predict with the theory, and it is working. But we have to take into account a very important aspect with biological samples, because it is when we illuminate your sample, we are plugging a very important photon flux into it. And if this continues for a long time, we may modify the structure of the sample. This is what is technically called photobleaching. And it is an aspect to take into account whenever we fluorescent. So it is important to try to reduce the illuminated area and the energy that we put. And finally, the main limitation is related with translucent materials. It means when we illuminate a material of this type, it often happens that we have a signal that we don't know where it comes from. If it comes from backscattering, if it is from fluorescent in the focal plane. So if we have fluorescent in the whole sample, it is worth to identify where it comes from. So in short, we have a technique for making image that is perfectly valid, but it has some problems. First, such short wavelengths make it impossible to go very deep into the layer of the tissue. As we have scattering that scales like 1 over lambda 4, scattering means all the photons that in some way we are reflecting. And this causes us to have a lot of noise in this image. On the other hand, the photo bleaching, we break the whole sample before we can make an image overall. Besides, this has another disadvantage. When we are illuminating the whole sample, the signal that we are receiving is from the focal plane and also from the surrounding plane. So we have to somehow get only the illumination of the focal plane. Even so, we have a lot of signal from the background that blurs the image. Also, other limitation is about the little soul shift. Makes that we can differentiate the excitation wavelength with the emission ones. So there's a lot of signal that we don't know if it comes from the source or from the sample. And finally, the most important in visual optics is about making an image in translucent material. Because we illuminate the cornea, when we illuminate the cornea, we don't know about the signal that we are receiving, if it is from the backscatter or from the fluorescent. These problems are what the multiphoton techniques are trying to solve. This is why we go to nonlinear interactions. Although the electric field is stronger if we use it, but if we use it in a correct and intelligent way, it can help us to make image. In the nonlinear process, one of the things they all have in common is that excitation frequency is completely different from the emission frequency. In fact, this emission frequency will be 2 or more times the excitation fluorescence frequency. We are going to focus on the two-photon absorption process, which is a generalization to the two photons of the typical fluorescent. In fact, it is called a two-photon excited fluorescence. In this equation here, we can perfectly differentiate the two principal terms, the linear part, this is the response of the electric field, and the nonlinear part. So clearly we can see that we need a lot of energy to take into account this term, because the level 2 susceptibility tensor have 5 orders of magnitude less than the level of 1 susceptibility. Also, there are other processes like second harmonic generation, third harmonic generation, and coherent anti-histogram scattering that follows the same idea. The main difference is that in second harmonic generation and the others, we can excite the electrons to a virtual state. This means that we don't need to go to an excited state, so we have more tunability for the wavelength. Also, there are several different differences between second harmonic generation and two-photon emission fluorescence, but we will not enter in much detail. Therefore, what must be clear to us is that, first, these processes are not common in nature because of their low probability. And the intense electric field that we need to apply. And second, the input and output frequency are totally different. For this talk, we are going to focus only in the two-photon excitation fluorescence. That is the generalization of linear fluorescence. The idea now is the same as before. The electron jumps from the fundamental layer to an excited state. But now, with the help of two photons, it means the electron takes the energy of the two photons to rise to the excited state. These two photons have to be less energetic than in conventional fluorescence. In fact, the sum of their energy at least has to give the difference of the state energy. One of the main advantages is that the energy is not necessary, has to be the exact difference. And here we will we will take into account only the return processes in which we go from the excited state to the fundamental state. This is what we call two-photon excited fluorescence. We go to the excited level with the help of two photons and arrive to the fundamental, emitting one other photon. For this process to be possible, the two photons have to arrive at the same time and at the same place. And this sentence will be very important to investigate how we can overcome this limitation of two-photon fluorescence. In linear fluorescence, we have already said that the excitation and the emission have a small Stokes shift. Of course, now the photons that we emit towards the sample are totally different from the ones that we receive. In fact, normally we will use the incident photons are in the infrared spectrum. This causes that the difference between emission and excitation is very large. So we do not have to worry about the Stokes shift. We have solved the first of the problems that we had in conventional fluorescence. But there is also another very interesting part of the two-photon excited fluorescence. And it is in order to be able to produce the fluorescence, we need to have many photons in a very small area, so that a couple of them access the condition that makes that fluorescence takes place. This is normally done by focusing the beam and the area where it is focused, which we technically call the Rayleigh range. Is the only place in the sample where fluorescence occurs. What advantage does this give us? Well, photobleaching is only from the area where we are focusing, as there is no fluorescence in the whole sample. Firstly, there is no photobleaching in the whole sample, only in the points where we are focusing, and secondly, all the fluorescence that we have, that is all the signal will come from the focal plane. So we reduce a lot of noise from the surrounding areas. And also, we overcome the problem of translucent material because the fluorescent light, it is not from the backscattering only. Only can be from the focal point. Let's compare the two techniques that we have now. As we see, the James-Blonsky diagrams are very similar. The only considerable difference is the fact that we break the excitation into two photons. And this is what changed the whole process. In fact, here we see how the excitation energy in both is the same. We don't put more energy, but the same in a more smarter way. In addition, the photobleaching that occurs in a single photon, as we see, is too much. This is indicated in the image of the bottom left, which is black and green. When we illuminate with a single photon, darkness the entire area around. It means it's producing fluorescence in all adjacent areas, and therefore we have photobleaching in all areas. However, in two-photon excitation, we only have photoleaching in the areas of the focal point. So a summary of what we are making on two-photon fluorescence is: by using two photons, we are using longer wavelength. Then we have less scattering. As we said before, the scattering goes like 1/λ4. So the longer the wavelength used, less scattering we have. This is basically the reflected photons that don't get absorbed. Thanks to this, we can go deeper into the tissue. So we enhance penetration depths. Imagine that we want to visualize a cell, and we see linear fluorescence, we can only see the superficial part. Well, now with this technique, it allows you to see the nucleus. Another very interesting advantage is that by having a large change in the wavelength of emission and excitation, we are achieving no overlap in the emission and absorption curves. So we can perfectly differentiate the photons that come from the sample and those that don't. Besides, the fact that there is no fluorescence around makes that all the signal can be said to be from the focal plane. But in the other hand, there are some disadvantages. This probability to generate this process is very low, so we have to increase the flux of photons in the focal plane, which makes photobleaching very fast due to the intensity we are putting it. This is a problem that could only be solved if we lower the power. So we are angry because we improved the technique of linear fluorescence, but also have other problems. So how do we overcome the disadvantage of low probability? It's mean the very high intensity that we are putting it. This is the question that we have to ask yourself. We know that the technique is good and it has solved the problems we had in a single fluorescent, but we still have to work on it. That's why the question that the researcher has to ask himself come. If we have said that to take place these processes, they have to reach the sample at the same time and at the same place, why don't we send the photons in groups? That is, why don't we set them in a more intelligent way that make this process takes place? Well, this is the idea that we want to check. In a technical language, that the photons are grouped together is also called bunching. And we need the photons to arrive at the sample in bunches. In the following slides, I'm going to explain what the bunching effect is, but this is a key to overcome the limitation of two-photon excitation fluorescence. So it's okay. It's okay. We need bunching, but how we can generate this? In 50s, Hambury, Brown, and Twist proposed an experiment in which they did interferometry, but with intensity. They used it to calculate the radius of the stars, and they were measuring what is called the second degree of coherence. We only need to know that this is a measure of correlation. So that the photon arrive in bands, this factor has to be equal or greater than 2. With thermal light, it can be equal to 2. With this idea, we are interested in obtaining sources that have a correlation greater or equal to 2. So we can characterize different sources by measuring this correlation. The way in which photons are emitted, and therefore their statistical properties, are very important. Therefore, we are going to describe now 3 different forms that will help us to understand the concept. The first one is a thermal source, where the particles that are emitted, that is, the photons, go in pairs, or rather in groups. These have been generated in this way and have an entanglement property that will be very important. The second source is related to the coherent source. That is to say, the laser source. As we know, the coherent source states that are usually called semi-classical states have the property that detecting them will give us the average value of photons that the system has. These are emitted in a random way. Therefore, there can be groups or not. In general, if we look at a time interval and we do the average, we will see that the average remains constant. And the third is a quantum source, a source that could be a Fock state, with the number of states well defined. In other words, we could say that photons are emitted one by one. What has to be clear is that the bunching effect is the sending of photons in groups, either two or more. And how to measure it? Although the background of the experimental and the physics in this is very deep, but we can simplify it in the following with the Hamburg-Brown and Twist interferometer. We have a beam of photons that is a source that passes through a beam splitter. And this beam splitter, we can simplify it as a half mirror that reflects part of the light that arrive to it and transmit the another part. With this idea, we could think, well, if I have a large flux of photons, the half part will go to the one detector, and the other half part will go to the another detector. Yes, this is what happened, but let's think it with a very few photons, with only one photon. It also reflects or transmits, but it cannot do both. Then one of the detectors will count, and the other will not count. But now let's think the next step about with two photons. There are three possibility states: two photons in one detector, two photons in the other detector, or one in each detector. And this is what is happening: that the probability of having one in each detector is greater than the other, and therefore this bunching effect will be benefited. Basically, the experiments count the photons that reach to the detector and the time difference between them. In this slide, what we represent is the idea of bunching with particles. As we have said before, a source thermal light emits by groups of photons. It's being by bunching. This is what we see in figure A, a thermal source with a Hamburg-Brown Twist interferometer in which we measure its correlation. And we see that for a delay of 0, the curve is asymptotic, meaning that the pairs of photons arrive at the same time at the two detectors. This type of source, this is the type of source that we want. We want many photons at the same time and at the same place. So if we generate them in a way that they arrive in a bunch, we will have a greater efficiency, and we will be able to reduce the intensity. As we see, there are other types of sources, such as laser sources, in which photons are emitted in a random way. That this makes the coincidence in the detectors totally uniform, and we don't see any type of variety, in these sources. And finally, there is a type of source in which we send the photons on one by one. We can interpret it as that the photons arrive at the beam splitter one by one. Then they only have two possible states, as we said before. But they only have two possible states, one detector or the other, but never both. That is why we have that the peak of coincidence goes to 0 with time delay, because we are never going to have two photons that arrive at the same time at the detector. With all of this, what I mean is that it is an experiment to know the statistical properties of the photons that arrive from the source, and this is what we will use to take for two photon excited fluorescence. In the last years, some experiments with thermal lights have been made, in which the idea previously shown is used to use the bunching of thermal lights to produce the two photon emission fluorescence. With this, also, they do not have an extraordinary bunching, only a factor of 2, a normal thermal light. Even so, they already managed to see the effects of this second degree of coherence, the correlation, seeing that it is improved in a factor that is proportional to the correlation. What does this mean? Is that the bunching effect can be confirmed experimentally, and that we are really right sending the photons in an intelligent way. Makes the two-photon excited fluorescent improve. In fact, what they are doing here is compare coherent light, which will be light from a laser source, with the lights coming from a normal thermal source. So the next step is, what if instead of use a factor we use a factor much larger, 2 order of magnitude or something like that? The latter is called superbunching. The idea is that instead of reaching a degree of correlation of only 2, why not to do it to higher? This is what is known as superbunching. And right now, several techniques are being investigated to generate them, creating a kind of artificial pseudo-thermal light. It's been with certain devices produce this effect with diffusor or something like that. And this is what some research, thanked et al. His company, observed in 2017. They could obtain a light with these characteristics, and that could be having superbunching. In the figure on the left, we have a measure of the correlation in 3 steps, and we see how the increase a level of 2 with several round glasses. 2, 4, 8, okay. So the next step, therefore, will be to test this type of superbunching source and check experimentally that you get an increase of 2 photon excited fluorescence of such level. And this is what we are working on. We are working right now in my master thesis. To finish my talk, I review the take-home message. So we are creating a new technique that meets all the requirements. That is, the two-photon fluorescence is a nonlinear technique requiring high intensity. Takes away all the limitation that we had in conventional fluorescence. It's been low signal from background and long and wavelength, but we have to use high intensity. The fact of having high intensity limits these techniques for all or biological studies or visual optics. So we can't use this for this process. In addition, we overcome this limitation of two-photon fluorescence with bunching that reduce the intensity required. So we will have achieved an efficient technique to generate images with multiphoton. And this is all from me. I hope you like it and you understand most of the presentation. Finally, keep safe in this time of coronavirus. And if there are any questions, I will be happy to answer them.
Okay, thank you very much for the presentation. It's been very interesting.